The universe is a racetrack beyond anything we could build here on Earth, where entire stars get flung across galaxies like cosmic bullets, and jets of plasma scream through space at nearly the speed of light. Today, we're counting down 50 of the most mind-blowing speed demons in the cosmos, from runaway stars that could cross our solar system in mere hours to black holes that catapult matter faster than anything nature should allow. Buckle up, because these aren't just fast objects, they're the universe's ultimate rule breakers, defying physics as we know it, and you're about to witness their secrets. At the top of our list is a cosmic speed demon that defies common sense, a neutron star spinning so fast its surface is moving at nearly a quarter of the speed of light. Meet Pulsar J1748-2446AD, the fastest spinning pulsar ever discovered. This crushed stellar corpse whirls 716 times every single second, meaning if you were standing on its surface, which you absolutely couldn't survive, you'd experience a full day in less time than it takes to blink. These extreme rotations happen because when a massive star collapses into a neutron star, it preserves its original angular momentum, but crammed into a ball just 12 miles wide. Imagine a figure skater pulling in their arms to spin faster. Now multiply that by a factor of several billion. The result is a mind-boggling density where a single teaspoon of its material weighs 1 billion tons, and magnetic fields trillions of times stronger than Earth's carve out beams of radiation that sweep across space like a lighthouse. This isn't just fast, it's nature pushing the limits of physics to the absolute extreme. Next up is one of the most violent phenomena in the universe, jets of superheated plasma screaming across space at nearly the speed of light. At the heart of Galaxy M87, a supermassive black hole launches a relativistic jet so powerful, it stretches over 5,000 light-years into the void. These aren't just cosmic fire hoses, they're particle accelerators on a galactic scale. When Hubble Space Telescope captured this jet in stunning detail, it revealed something even stranger. From certain angles, the material appears to move faster than light itself. How? It's an illusion caused by the jet's insane speed combined with our viewing angle. As the plasma barrels toward us at 99% light speed, its light gets compressed like a cosmic Doppler effect on overdrive. But the real magic happens when space-time itself twists around the jet. Einstein's relativity tells us that anything moving this fast warps the fabric of the universe around it, bending light and distorting our perception. The energy behind these jets is almost unimaginable enough to outshine entire galaxies. And here's the craziest part, we're seeing this unfold from 55 million light-years away, meaning the light reaching us today left when dinosaurs still roamed Earth. That's the sheer scale of cosmic speed we're dealing with. Some stars don't just move fast, they're flung out of their home galaxy entirely. Take S5HVS1, a hypervelocity star racing through space at 1,755 kilometers per second, fast enough to cross the entire United States in less than 2 seconds. This cosmic runaway didn't get its speed from a typical stellar explosion. Instead, it was catapulted by the monstrous gravity of Sagittarius, a star, the supermassive black hole at the heart of our Milky Way. Here's how it happened. When a binary star system wandered too close to the black hole, one star got captured while the other was slingshotted away with enough velocity to escape our galaxy forever. Now, S5HVS1 is on a one-way trip into the vast emptiness between galaxies, where it will drift for billions of years, untouched by any star cluster or planet. Unlike most stars bound to galactic orbits, hypervelocity stars like this are destined to become permanent wanderers, lonely travelers in the dark. And they're not just fast, they carry crucial clues about the extreme environments near supermassive black holes. Each one we discover helps us map the invisible forces shaping our galaxy's core. Imagine being ejected with such force that nothing, not even a galaxy's gravity, can pull you back. That's the raw power of these stellar speedsters. Picture a cosmic hurricane so powerful, it could rip apart 1,000,000 suns, then crank that violence up 100-fold. That's the reality of quasar outflows, where superheated gas blasts through space at 1/5 the speed of light. At the center of this maelstrom sits SDSSJ 1106+1939, a quasar whose record-breaking winds carry more energy every year than our Sun will produce in its entire lifetime. These aren't just gusts, they're galaxy-altering tsunamis. When material spirals into the supermassive black hole powering the quasar, friction heats it to millions of degrees, creating pressures so extreme that gas gets catapulted outward like a cosmic cannon. The numbers defy belief: 40 trillion times the Sun's luminosity, winds hitting 20,000 kilometers per second, and enough force to blow entire star-forming regions into the void. What's truly wild, these outflows don't just destroy, they create. By clearing away ancient gas clouds, they force galaxies to evolve, shutting down star formation and sculpting the universe's large-scale structure. It's a reminder that even the fastest objects in the cosmos aren't just racing, they're rewriting the rules of existence itself. Strap in for something that sounds straight out of science fiction: a supermassive black hole racing through the cosmos so fast, it's dragging a 200,000 light-year long trail of newborn stars behind it like a cosmic paintbrush. Hubble spotted this runaway monster, dubbed 3C186, barreling through its galaxy at a jaw-dropping 7.5 million miles per hour. That's so fast it could cross the distance from Earth to the Moon in just 3 minutes. But how does something with billions of times the Sun's mass get kicked into overdrive? The answer lies in one of Einstein's wildest predictions: gravitational wave recoil. Picture two supermassive black holes locked in a death spiral, orbiting each other closer and closer until they finally merge. If their collision isn't perfectly symmetrical, the resulting blast of gravitational waves can rocket the newly formed black hole in the opposite direction, like a cannon firing backward. The recoil from this cosmic kick sends the black hole careening through space, plowing through gas clouds and triggering star formation in its wake. Those glowing blue streaks Hubble captured. They're clusters of young stars ignited by the shockwaves of the black hole's escape. It's a rare glimpse of nature's raw power, where even the darkest, heaviest objects in existence can become cosmic fugitives. And here's the mind-bending part: 3C186 is already 25,000 light-years from its galaxy's center. By the time its light reaches us, it might have already escaped entirely, a dark giant forever adrift in the void. Now let's zoom in on a cosmic dance so rapid it defies belief: a pair of white dwarfs locked in the tightest, fastest orbital embrace ever discovered. Meet HM Cancri, a binary system where two dead stars whirl around each other at a staggering 1.8 million kilometers per hour, completing a full orbit every 5.4 minutes. That's faster than a bullet fired from a rifle, meaning if you could watch this system up close, you'd see these stellar corpses streaking through space like frenetic marbles on an invisible track. These white dwarfs are so close together, their entire orbit could fit inside the diameter of Earth, a cosmic waltz compressed into a space smaller than our planet. But here's the twist: their breakneck speed isn't just a spectacle, it's a preview of one of Einstein's greatest predictions in action. Each orbit ripples spacetime itself, sending out gravitational waves that slowly sap their energy, drawing them even closer. In about 340,000 years, a blink in cosmic time, they'll collide in a titanic explosion, possibly triggering a supernova or merging into a single, bizarre stellar remnant. What makes HM Cancri truly special is how it serves as a real-life laboratory for extreme physics. Astronomers use its flickering light like a cosmic stopwatch to measure the subtle effects of relativity, proving that even in death, stars can teach us about the universe's deepest mysteries. Imagine two city-sized objects, each heavier than our Sun, moving fast enough to circle the moon in under 40 seconds. That's the raw, dizzying speed of this record-breaking duo. Deep in the cosmos, an explosion so violent erupted that it temporarily blinded our most sensitive gamma-ray detectors, a cosmic event astronomers nicknamed the BOAT, short for brightest of all time. This monster, officially catalogued as GRB 221009A, unleashed jets of matter screaming through space at 99.999% the speed of light. To grasp how insane that is, if these jets raced against a beam of light itself, they'd lose by just 300 kilometers per hour. These aren't your garden variety space phenomena. They're the universe's ultimate particle accelerators, powered by the catastrophic collapse of a massive star into a newborn black hole. What makes these jets truly defy logic is something physicists call the Lorentz factor, a mind-bending number describing how time and space warp at such extreme velocities. For the BOAT's jets, that factor soared above 1,000, meaning time for those particles crawled nearly to a halt compared to our perspective. Imagine watching a clock aboard one of those jets. It would tick just once while centuries passed here on Earth. This time dilation isn't science fiction. It's Einstein's relativity in its most extreme form. Yet the real shock came when astronomers realized these jets weren't perfectly aligned with Earth. We were seeing them slightly off-axis. That's like catching a lighthouse beam from the side and still getting seared by its brilliance. The energy released was so incomprehensible, it rewrote our understanding of what's physically possible in stellar deaths. In mere seconds, this single burst outshone the combined light of every star in a million Milky Ways. But here's the haunting twist. The star that birthed this cataclysm died over 2 billion years ago. Its light and its final, furious scream only reached us now, echoing across epochs. It's a reminder that when we witness these cosmic speed demons, we're not just watching physics pushed to its limits, we're peering into the universe's capacity for raw, unfiltered violence. Here in the cosmic demolition derby, entire galaxies don't just collide, they rip through each other with enough force to bend the laws of physics. Take the Bullet Cluster, two galaxy clusters caught in a cataclysmic head-on collision, where the shockwave alone races outward at 100 million miles per hour, Mach 1000 plus. That's not just supersonic, it's a pressure wave so violent it could cross the Atlantic Ocean in under a second. But this cosmic wreckage holds something even more extraordinary, the first direct proof of dark matter's ghostly grip on the universe. When these titanic clusters smashed together, their visible gas, heated to millions of degrees, slammed into a traffic jam of particles, creating that searing shock front. Meanwhile, something bizarre happened to the cluster's mass. By mapping gravitational lensing, astronomers saw most of the weight wasn't where the gas glowed. It had sailed ahead, invisible. That mismatch revealed dark matter's signature, a substance that doesn't emit light or slow down, plowing through normal matter like a phantom freight train. This wasn't just a collision, it was a smoking gun showing dark matter really exists, and it's out there sculpting the universe while remaining utterly unseen. The Bullet Cluster is more than a speed record. It's a cosmic crime scene where the clues rewrite everything we know about reality. Meet the fastest known pulsar in our galaxy, PSRB 2224+65, a stellar corpse hurtling through space so fast it could cross the distance between Earth and the Moon in just 6 minutes. Nicknamed the Guitar Nebula Pulsar for the 37 light-year long wake of energized particles it leaves behind, shaped like a cosmic guitar string vibrating through the void, this neutron star rockets at 1,600 kilometers per second. That's roughly 5 times faster than most pulsars, and scientists believe its breathtaking speed came from a violently uneven death. When its parent star exploded as a supernova, the collapse wasn't symmetrical. Imagine a firework bursting with more force on one side, the recoil would send it careening in the opposite direction. That's exactly what happened here, a natal kick so powerful, it launched this pulsar like a cosmic cannonball. The shockwave from that ancient explosion didn't just propel it, it also left behind that stunning guitar-shaped trail, created as the pulsar's powerful magnetic field and particle winds slam into surrounding gas, lighting it up like a neon sign in space. What's fascinating is how these extreme speeds help astronomers piece together supernova explosions we'll never witness directly. Each runaway pulsar is a fossil record, a silent witness to the chaos of stellar death, still racing away from the scene millions of years later. And the Guitar Nebula pulsar, it's not slowing down. One day, it'll escape the Milky Way entirely, becoming a lone traveler in the dark between galaxies, a rock star without a stage, forever strumming the vacuum of space. Our solar system might feel like home, but breaking free from its gravitational grip requires blistering speed, something even our fastest human-made objects barely achieve. Take New Horizons, the spacecraft that gave us our first close-up of Pluto. It raced away from Earth at 16 kilometers per second, so fast it could cross the continental United States in under 5 minutes. Yet that's still slower than its older cousin, Voyager 1, which clocks 17 kilometers per second after getting a lucky gravity boost from Jupiter and Saturn. These numbers sound impressive until you realize they're barely a fraction of what nature routinely accomplishes. Hypervelocity stars flung by supermassive black holes can hit speeds over 1,000 kilometers per second, fast enough to leave our entire solar system in the dust before you finish lunch. But what if we could harness light itself for interstellar travel? Enter Solar Sail's theoretical spacecraft designed to ride sunlight like cosmic surfboards. Current prototypes envision speeds up to 20% light speed, meaning a sail-powered probe could reach Alpha Centauri in just 20 years. Compare that to Voyager, which would need 70,000 years for the same trip. The key lies in momentum. Photons from stars carry tiny pushes, but over time, those gentle nudges add up to staggering velocities, no fuel required. It's a reminder that in the race to conquer cosmic distances, sometimes the slowest forces like sunlight hold the keys to the fastest journeys. Here's the twist: even solar sails would pale next to nature's true speedsters. While we meticulously calculate escape velocities, the universe casually flings stars like slingshot projectiles. That's the humbling scale of cosmic motion, where our greatest engineering feats are just the first timid steps into a realm where speed is measured in percentages of light itself. While the universe flings stars and black holes at unbelievable speeds, humanity has its own speed champion pushing the boundaries of physics right in our solar system. The Parker Solar Probe isn't just breaking records, it's rewriting the playbook for space travel. In 2021, this car-sized spacecraft screamed past the Sun at an astonishing 692,000 kilometers per hour, making it the fastest human-made object in history. To put that in perspective, at peak velocity, it could zip from New York to Tokyo in under 20 seconds, but raw speed isn't even the most impressive part. The real genius lies in how it got there, using Venus like a cosmic slingshot. Each graceful swing past the planet steals a fraction of its orbital energy, flinging the probe closer to the Sun with exponentially increasing velocity. It's like a skateboarder grabbing a moving car's bumper to accelerate, except here the car is an entire planet. And then there's the shield, a marvel of engineering that lets Parker survive temperatures hotter than lava while its instruments stay cool enough for ice cream. This 8-foot-wide carbon composite disc withstands 2,500 degrees Fahrenheit, all while the spacecraft's shadow creates its own microclimate of near-room temperature. Without this technological umbrella, the probe would vaporize faster than a snowflake in a blast furnace. What's truly remarkable is how this mission turns the Sun's own fury into an advantage. As Parker dives just 6 million kilometers above the solar surface, 7 times closer than Mercury, it's harvesting data that could revolutionize our understanding of solar winds and space weather. Every gravity assist, every blistering pass, brings us closer to unlocking secrets that have baffled scientists since the dawn of astronomy. Think about it. While nature's fastest objects rely on black holes and supernova for acceleration, we've harnessed orbital mechanics and materials science to touch the edges of stellar velocities. Parker isn't just fast, it's proof that even in a universe of cosmic speed demons, human ingenuity can still leave its mark. And with future flybys planned, this record won't just stand, it'll shatter. Here's something that puzzled astronomers for decades. Why do stars on the Milky Way's outer edges whip around at 250 kilometers per second when basic physics says they should be slowing down? Picture a carousel where the horses on the outside somehow spin just as fast as those near the center, despite having farther to travel. That's exactly what happens in our galaxy, and the answer lies in an invisible cosmic scaffold, dark matter. The trouble started when scientists calculated the Milky Way's rotation curve, a graph showing how orbital speeds change with distance from the galactic core. Newtonian physics predicted outer stars would crawl compared to inner ones, like planets moving slower in our solar system's icy outskirts. Instead, the curve stayed suspiciously flat, meaning stars far from the center were zooming along just as fast as their inner siblings. Then came the real head-scratcher. Even adding up all the visible matter, stars, gas, dust only accounted for a fraction of the gravity needed to explain those speeds. Enter dark matter, the universe's hidden architecture. This mysterious substance doesn't emit or absorb light, but its gravitational pull wraps galaxies in an invisible halo, anchoring those speeding outer stars like an unseen hand guiding a spinning top. But here's where it gets weirder. There's also a missing baryon problem. Baryons are normal matter particles like protons and neutrons, and based on cosmic surveys, about half of them are unaccounted for in the Milky Way. Some might be hiding as faint, hot gas between galaxies, but their absence deepens the rotation mystery. It's like realizing your car's speedometer is broken, then discovering half the engine parts are gone too. What makes this so thrilling is how it reshapes our cosmic map. Dark matter isn't just some abstract idea, it's the reason our galaxy holds together at these insane speeds without flinging stars into the void. And those missing baryons, they're a reminder that even the familiar universe still keeps secrets. So next time you gaze at the Milky Way spiral arms, remember, you're looking at only a fraction of the story. The rest moves in the dark. Galaxies usually move like grand, slow-motion pinwheels, graceful spirals turning over hundreds of millions of years. But sometimes the universe cranks the dial to ludicrous speed. Enter NGC 7674, a spiral galaxy spinning so fast its outer arms whirl at 4.5 million miles per hour. That's fast enough to cross the entire United States in less than a second. Hubble's sharp eyes caught this cosmic speedster in action, revealing a spiral stretched to its breaking point. Like a merry-go-round spinning so violently, its edges nearly fling stars into the void. So how does a galaxy reach these extreme velocities? The answer lies in a high-stakes cosmic merger. Billions of years ago, NGC 7674 likely collided with another galaxy, an event so violent it injected a surge of energy into the system. Think of it like stirring a cup of coffee with a spoon. The swirling motion accelerates the liquid. Only here, the spoon is an entire galaxy smashing through, and the coffee is a sea of stars and gas whipped into frenzy. The aftermath left NGC 7674 with an overactive core, a supermassive black hole devouring material so voraciously it energizes the entire disk, forcing the outer arms to keep pace with the inner chaos. But here's the twist. This breakneck spin isn't just a spectacle, it's reshaping the galaxy's future. At these speeds, gravity struggles to hold everything together. Gas clouds that might have formed new stars get flung outward, while others spiral inward, feeding the black hole's insatiable appetite. It's a self-perpetuating cycle, the faster the spin, the more material gets funneled to the center, which in turn fuels even faster rotation. What's truly mind-bending is how common this might be. Hubble's deep field surveys suggest up to a quarter of spiral galaxies could be hiding these extreme rotations, quietly spinning at velocities that defy expectations. NGC 7674 is just one visible example of a universe where even the grandest structures have a need for speed. And when you realize this whirlwind spans 120,000 light-years, the sheer scale of its motion becomes almost incomprehensible, a cosmic hurricane where entire star systems ride the winds. In the vast emptiness between galaxies, a single subatomic particle once screamed through space at a velocity so extreme, it redefined what we thought was possible. Meet the "oh my god" particle, a cosmic ray detected in 1991 with energy so incomprehensible, physicists initially doubted their instruments. This proton, smaller than an atom, packed the kinetic energy of a baseball thrown at 60 miles per hour, all while hurtling at 99.9999999999999999999999999999999999999999999999999999999999999999999999999999999 the speed of light. Just how close to light speed is that? If this particle raced a beam of photons from the moon to Earth, it would lose by less than the width of a human hair. What's truly baffling is how anything could reach such energies. Normally, cosmic rays gain speed from supernova shockwaves or pulsar winds, but this particle's energy was millions of times beyond what those processes should produce. Some theories suggest it might have been flung by an active galactic nucleus, where a supermassive black hole's magnetic fields act like a cosmic railgun. Others speculate it could be evidence of exotic physics like decaying super-heavy dark matter particles or defects in spacetime itself. Here's the kicker: when this proton hit Earth's atmosphere, it triggered a shower of secondary particles so intense it would have been visible to the naked eye had anyone been staring at the right patch of Utah sky that night. And that's the haunting beauty of ultra-high-energy cosmic rays. They're invisible messengers from the universe's most violent corners, carrying secrets we're still deciphering decades later. The mysteries don't stop there. Since 1991, detectors have spotted a handful of similar particles, each one a cosmic lightning bolt with no clear origin. They're reminders that even at the smallest scales, the universe operates with a ferocity we've barely begun to understand. And somewhere out there, another "oh my god" moment might already be streaking toward us, a silent speck of matter carrying the energy of a star. Among the thousands of exoplanets discovered, one stands out not just for its speed, but for the way it's being torn apart by its own velocity. WASP-12b isn't just the fastest exoplanet we know, it's a world stretched to breaking point, whipping around its star in a death spiral so tight, a full year there lasts just 26 hours. Picture a gas giant like Jupiter, but so close to its sun that its atmosphere is being literally cooked away at 2,200 degrees Celsius. This planet hurtles through space at 225 kilometers per second, fast enough to circle Earth's equator in under 3 minutes. That blistering speed, combined with the star's monstrous gravity, has deformed WASP-12b into a teardrop shape, like cosmic taffy being pulled apart. Infrared observations reveal the gruesome details. A vast plume of superheated gas, ripped from the planet's outer layers, forms a swirling tail stretching hundreds of thousands of kilometers into space. This isn't just a hot Jupiter, it's a dying one, losing the equivalent of 3 Earth masses every billion years to its hungry star. What's truly eerie is how this doomed world warps time itself. Orbiting so close to its star, tidal forces have locked one side in perpetual daylight, creating a hemisphere of molten rock vapor, while the night side glows dull red from residual heat. The temperature difference between these two faces could power storms more violent than anything in our solar system. But here's the twist: WASP-12b won't vanish quietly. Current models suggest it has maybe 10 million years left before the star's gravity shreds it completely, a blink in cosmic terms. Until then, it serves as a grim laboratory, showing us how extreme environments can reshape worlds beyond recognition. A reminder that in the universe, even the fastest objects can't outrun fate forever. The aftermath of a supernova isn't just an explosion. It's a cosmic shotgun blast firing stellar shrapnel across space at unimaginable speeds. Take Cassiopeia A, the shattered corpse of a star that detonated around 300 years ago. Chandra X-ray Observatory captured something breathtaking here: knots of debris rocketing outward at 15 million miles per hour, fast enough to cross Earth's orbit in just 40 minutes. These aren't just random chunks of stellar wreckage. They're elemental bullets packed with forged metals from the star's violent death throes. What makes these hypersonic fragments so special is what they carry: heavy elements like silicon, iron, and oxygen, cooked up in the supernova's furnace and now being injected into the galaxy. Imagine a celestial fertilizer spreading the ingredients for future stars, planets, and even life itself. Each glowing knot seen in Chandra's images is essentially a time capsule, preserving the exact conditions of that final catastrophic moment when the star tore itself apart. But here's what's wild: this debris isn't slowing down. Unlike typical explosions where material eventually decelerates, these knots are surfing on shockwaves generated by the supernova itself, accelerating even as they travel. Some are so dense they punch through surrounding gas like cosmic cannonballs, leaving turbulent wakes visible in X-ray wavelengths. And buried in these speeding fragments is a bigger story. The same process that flung them across space also created the very atoms that make up our bones, the iron in our blood, and the oxygen we breathe. We're literally built from stardust hurled at these extreme velocities billions of years ago. So when we watch Cassiopeia A's debris racing through space, we're not just witnessing destruction, we're seeing the universe's way of rebuilding itself, one supersonic spark at a time. Deep within the giant elliptical galaxy M87, a rogue star cluster made history by becoming the fastest-moving group of stars ever discovered. HVGC1, hurled outward at a staggering 3.4 million miles per hour. That's fast enough to reach Pluto from Earth in just 5 days. This isn't just a galactic speed record, it's a cosmic crime scene with a supermassive black hole as the prime suspect. Here's how this stellar heist unfolded. HVGC1 was once an ordinary globular cluster, a dense ball of ancient stars orbiting M87's center. But when it drifted too close to the galaxy's central black hole, a monster weighing 6.5 billion suns' gravity played a brutal game of celestial billiards. Astronomers believe a rare three-body interaction occurred, two black holes orbiting each other near the galactic core, with HVGC1 passing dangerously close. The combined gravitational kick acted like a cosmic slingshot, flinging the entire cluster outward while conserving momentum from the black hole's dance. What's astonishing is the energy required to eject not just one star, but hundreds of thousands bound together by gravity. Typical hypervelocity stars escape solo, torn loose when their binary companions get captured by black holes. But HVGC1's survival as an intact cluster suggests it was dense enough to withstand tidal forces that would rip apart looser groups. Imagine throwing a snowball through a fan. Most would disintegrate, but one packed tightly enough might emerge intact. This discovery rewrites our understanding of extreme environments near supermassive black holes. These regions aren't just destructive, they're particle accelerators on galactic scales, capable of launching entire star systems into intergalactic space. HVGC1 is now doomed to wander the void between galaxies, its stars shining far from any galactic home. And somewhere in its ancient light lies a message: even the universe's most violent neighborhoods can create unexpected cosmic fugitives. Somewhere in our galaxy, two dead stars perform the fastest cosmic waltz ever recorded, a mind-bending orbital dance where a full year passes in just 5 minutes and 21 seconds. Meet RxJ0806.3 plus 1527, a pair of white dwarfs whipping around each other at 1.8% the speed of light, so fast their gravity distorts spacetime itself. These stellar corpses, crammed into a space smaller than Earth's diameter, complete an orbit faster than a microwaved cup of coffee heats up. What makes this duo truly revolutionary is the song they're broadcasting across the cosmos, a faint but unmistakable chirp of gravitational waves. Einstein predicted these ripples in spacetime over a century ago, but RxJ0806 gives us a front-row seat to the phenomenon in action. As the stars spiral closer, their insane velocity, nearly 5,400 kilometers per second, sends out gravitational waves that gradually sap their orbital energy. Think of it like a spinning ice skater slowly pulling their arms in, except here the arms are tidal forces powerful enough to shred planets. Here's where it gets wild. Every year, their orbit shrinks by about 1.4 meters as those gravitational waves carry energy away. That might not sound like much, but extrapolate that over centuries and this system becomes a ticking time bomb. In roughly 300,000 years, these white dwarfs will collide, potentially triggering a supernova or merging into an even stranger stellar remnant. For astronomers, this binary is more than a speed freak. It's a natural laboratory for testing relativity under extreme conditions, that rhythmic chirp of escaping gravitational waves. It's the universe's metronome, counting down to a cataclysm that will illuminate one of space's greatest mysteries. And the most humbling part, this dizzying dance has been playing out unseen for millennia. Only now are we learning to listen. In the cosmic theater of sudden brightness, one star recently stole the show with a performance that left astronomers speechless. V1674 Hercules, the fastest nova ever recorded. While most stellar explosions take weeks to reach peak brightness, this white dwarf went from cosmic afterthought to celestial spotlight in just 1 hour, blazing with the energy of 50,000 suns before slowly fading. It's like a firework that ignites, explodes, and vanishes all before you finish a cup of coffee. What makes this flash so extraordinary lies beneath the star's surface. V1674 Hercules isn't just any white dwarf. It's a ticking thermonuclear bomb with perfect conditions for what scientists call a surface runaway. Here's how it works. The dwarf siphons hydrogen gas from a nearby companion star, letting it accumulate on its ultra-dense surface. As pressure builds, the hydrogen layer reaches critical mass, triggering a chain reaction that rips across the entire star in minutes. This isn't just burning, it's a full-scale nuclear detonation where temperatures spike to 100 million degrees, blasting the accumulated material into space at thousands of kilometers per second. But the real shocker, the aftermath. Most nova eject material relatively slowly, creating expanding shells that linger for years. V1674 Hercules defied expectations by flinging its debris outward at over 5,000 kilometers per second. So fast, the ejector formed bizarre, asymmetrical shapes instead of the usual smooth spheres. This suggests the explosion wasn't just violent, it was deeply unstable, possibly warped by the white dwarf's intense magnetic fields or rapid rotation. Here's what's truly groundbreaking. This event may rewrite how we classify stellar explosions. Traditional nova and supernova exist on a spectrum of violence, but V1674 Hercules occupies a strange middle ground, too fast for a typical nova, yet not destructive enough to obliterate the dwarf. It's a reminder that even in stellar deaths, the universe has surprises waiting, events that don't just break records, but challenge our very understanding of cosmic physics. And somewhere out there, another white dwarf might be preparing its own record-shattering encore. Wrapping around our galaxy like a cosmic lasso is one of the most breathtaking yet invisible structures in the local universe, the Magellanic Stream. This colossal ribbon of gas, stretching over 600,000 light-years, tears through space at an astonishing 1.1 million kilometers per hour, fast enough to circle Earth's equator in under 25 seconds. What makes this intergalactic river so spectacular isn't just its speed, it's the story written in its turbulent wake. Born from gravitational theft, this stream is the shredded remains of two dwarf galaxies, the Large and Small Magellanic Clouds, caught in a slow-motion tug-of-war with our Milky Way. Every pass they make around our galaxy strips away more of their gas, leaving this glittering trail across the cosmic ocean. Hubble's ultraviolet eyes revealed something unexpected. This gas isn't just drifting, it's supercharged, glowing with the energy of ancient stellar explosions that once rocked the Magellanic Clouds. But here's where it gets dramatic. That blazing velocity isn't just carrying gas, it's delivering it. Simulations suggest this stream will eventually rain down onto the Milky Way, fueling a new generation of stars in about 2 billion years. And the Magellanic Clouds themselves, their fate is sealed. Each orbit brings them closer to a collision course with our galaxy's outer halo, where they'll be torn apart entirely, joining the countless dwarf galaxies our Milky Way has already consumed. What's humbling is realizing we're witnessing a process as old as galaxies themselves. The Magellanic Stream isn't just a speedster, it's a vital link in the cosmic food chain, showing how even the smallest galaxies contribute to the growth of giants. And somewhere in that river of hypervelocity gas could be the raw materials for future solar systems, perhaps even ones with worlds like ours. Among the universe's speed demons, one underdog stands out: not a star, not a planet, but something caught between. The runaway brown dwarf known as 2-mass J0348-6022. Clocking in at 500 kilometers per second, this cosmic misfit streaks through space fast enough to cross Earth's diameter in under 30 seconds. What's wild isn't just its velocity, it's how it got there. Unlike pulsars slingshotted by supernova or stars ejected by black holes, this brown dwarf's speed comes from a far gentler yet equally violent origin, the nursery where it was born. Brown dwarfs are the universe's failed stars, too small to ignite nuclear fusion, yet too massive to be called planets. Most drift quietly through space, but 2-mass J0348 is different. Its blistering speed suggests it was flung outward during a chaotic stellar adolescence, when gravitational tugs of war between young stars in its birthplace cluster sent it careening into the void. Imagine being tossed from a cosmic game of dodgeball, except instead of a ball, it's an object 80 times Jupiter's mass hurled fast enough to escape its galaxy's grasp forever. Here's where the story defies expectations. Current models suggest brown dwarfs form like stars from collapsing gas clouds, but discoveries like this hint at a grittier truth. Some might originate like planets, born in protoplanetary disks only to be violently ejected by competing gravitational pulls. The speed of 2-mass J0348 supports this. It's not just moving fast, its trajectory points directly back to a region of active star formation, like a forensic clue left at the scene of its cosmic eviction. The real kicker, this brown dwarf isn't alone. Surveys reveal a growing population of these runaway failures, each one challenging our definitions of what separates stars from planets. And as they streak through the darkness, they carry with them a silent lesson. Sometimes, the universe's fastest objects aren't the brightest or the biggest, but the ones tossed aside by gravity's ruthless games. Floating just beyond our galaxy's edge, a colossal cloud of hydrogen gas is barreling toward the Milky Way at 300 kilometers per second. The Smith Cloud, a hypervelocity monster on a collision course with home. This isn't just any interstellar gas blob. It's a cosmic boomerang returning after a 70 million year exile that took it clear past the Milky Way's outer halo and back. Picture a river of hydrogen stretching 11,000 light-years long and 2,500 light-years wide, moving fast enough to cross the distance between Earth and the Moon in just 21 minutes. What makes this cloud so extraordinary isn't just its speed, it's the story hidden in its trajectory. observations from the Green Bank telescope reveal something startling. Despite its immense velocity, the Smith cloud isn't a foreign invader. Its chemical fingerprint matches the Milky Way's own outer gas layers, suggesting it was ripped away from our galaxy eons ago, either by a collision with another galaxy or a violent gravitational tug-of-war between dark matter clumps. Now it's hurtling back like a prodigal fragment, carrying enough hydrogen to birth 2 million suns. But the most breathtaking detail, the cloud's fate, is written in its own wake. As it plows through the Milky Way's halo, it's leaving behind a glowing trail of ionized gas, a celestial breadcrumb trail marking its journey. When it finally slams back into our galaxy's disk in about 30 million years, the collision could ignite a firestorm of new star formation, lighting up spiral arms with stellar nurseries. Here's the twist: this isn't just a one-off spectacle. The Smith cloud is a glimpse into the Milky Way's messy recycling system, where gas gets flung into the void only to rain back down later, seeding future generations of stars. And somewhere in that returning torrent of hydrogen could be the raw materials for planets, or even life, that don't exist yet. It's proof that even the fastest objects in our galaxy are part of a much larger, slower dance, one where everything eventually comes full circle. Not all stellar ghosts drift quietly through the cosmos. Some get violently kicked into hyperspace. Meet SDSS J0927 plus 2943, the fastest white dwarf ever clocked, racing through our galaxy at 2,400 kilometers per second. So fast it could lap Earth's equator in just 16 seconds. Unlike the graceful spins of pulsars or the slingshot escapes of hypervelocity stars, this white dwarf's insane speed comes from a cosmic catastrophe, a botched suicide attempt. When its parent star died, the supernova explosion wasn't symmetrical. Normally, these blasts eject material evenly, leaving behind a neutron star or black hole. But in rare, partial ejection scenarios, the detonation fires off lopsided like a firework with more gunpowder on one side. The recoil from that uneven blast can launch the remaining white dwarf core like a cannonball without completely destroying it. That's exactly what happened to SDSS J0927. It's essentially a stellar shrapnel fragment, still glowing from the explosion's residual heat. What makes this speedster particularly fascinating is its chemical fingerprint. Spectroscopic analysis reveals traces of elements normally found deep inside stars, proof it was violently stripped of its outer layers mid-explosion. It's as if the universe tried to erase this white dwarf but gave up halfway, leaving behind a wounded fugitive streaking through space. And here's the haunting part: this isn't just a fluke. Astronomers suspect dozens more of these supernova survivors could be hiding in plain sight, their extreme velocities masked by the Milky Way's crowded star fields. Each one is a fossilized imprint of a star's final, chaotic moments, a reminder that even in death, celestial objects don't always go quietly. They sometimes leave with a bang, a kick, and a one-way ticket to interstellar space. When it comes to particles pushing the speed limit, nothing beats neutrinos, the universe's ultimate speed demons at the subatomic level. In 2011, the OPERA experiment sent shockwaves through physics by detecting neutrinos that appeared to outpace light itself. Their measurements suggested these ghostly particles arrived 60 nanoseconds faster than photons over a 730-kilometer journey, a tiny difference with massive implications. For a brief moment, it seemed Einstein's cosmic speed limit had been shattered. But here's where quantum mechanics gets messy. Further analysis revealed the result was a fluke. A faulty fiber optic connection had skewed the timing data. Yet buried in that near miss was something profound. Even neutrinos, which barely interact with matter, can't cheat relativity. They come agonizingly close though, hitting 99.9999995% light speed, so fast if they raced a photon from the Sun to Earth, they'd lose by just 8 centimeters. What's wilder is why they're so quick. Unlike light, neutrinos barely notice the universe's obstacles. No electromagnetic drag, no scattering off interstellar gas, just pure, unfiltered motion. Some theorists even suggest they might slip through quantum foam, the hypothetical froth of spacetime at the smallest scales. If spacetime has tiny bubbles or wrinkles at the Planck level, neutrinos could be taking shortcuts photons can't. Yet here's the twist: their near-light-speed dance isn't just a physics curiosity. Neutrinos from supernova often outpace their own star's light, giving astronomers early warnings of stellar explosions. In 1987, detectors caught neutrinos from SN 1987, a full 3 hours before telescopes saw the flash, proof that even when playing by relativity's rules, these particles operate on a different clock. So while they didn't break Einstein's speed limit, they're still the closest thing we've found to nature's ultimate cosmic racers. Galaxies usually spin like elegant whirlpools, their spiral arms trailing gracefully behind. But NGC 4622 laughs in the face of cosmic convention. This bizarre galaxy doesn't just rotate. It's a celestial tempest where spiral arms spin in opposite directions at different speeds, defying everything we thought we knew about galactic motion. Most galaxies organize themselves neatly, with outer arms lagging slightly as they orbit the center. Not this one. Observations from Hubble revealed something downright surreal: a leading outer arm whipping around faster than the galaxy's inner disk, while another arm drags behind in the opposite direction. It's like watching a carousel where some horses charge forward while others gallop backward, a kinematic nightmare that shouldn't exist, the secret to this chaos. A violent past: astronomers suspect NGC 4622 collided with a smaller galaxy long ago, injecting so much turbulence that the resulting gravitational shockwaves twisted its structure inside out. Now the galaxy's outer arms blaze ahead at roughly 200 kilometers per second, outstripping the slower inner rotation by a significant margin. Meanwhile, gas and stars caught in the opposing arm get dragged backward, creating a dizzying celestial tug-of-war. What makes this galaxy truly special isn't just its odd rotation, it's the window it opens into galactic evolution. Normally, spiral arms are density waves, moving like traffic jams in a stellar highway. But NGC 4622's mismatched arms suggest a far messier reality, one where mergers can permanently scramble a galaxy's DNA. It's proof that even the grandest cosmic structures don't always follow the rules, and sometimes the fastest objects in the universe aren't just single stars or particles, they're entire swirling arms, racing against their own galaxy. In August 2017, the universe handed scientists a gift wrapped in gravitational waves and gamma rays: GW170817, the first confirmed kilonova collision ever observed. When two neutron stars slammed together 130 million light-years away, they didn't just shake spacetime, they blasted a jet of neutron-rich debris into the cosmos at nearly 30% the speed of light. That's over 300 million kilometers per hour, fast enough to cross our solar system in a matter of days. This wasn't just any cosmic debris, it was a nuclear alchemy lab running at full throttle. The extreme conditions forged heavy elements like gold, platinum, and uranium in real time, solving a decades-old mystery: where half the universe's precious metals come from. A single teaspoon of this ejector would weigh billions of tons and contain enough gold to outshine Earth's entire reserves. What made this event revolutionary wasn't just the speed or the sparkle, it was how we witnessed it. For the first time, humanity caught the same celestial cataclysm through multiple senses. Gravitational wave detectors felt the space-time ripples, telescopes saw the afterglow, and satellites even picked up gamma-ray bursts just seconds later. This trifecta, dubbed multi-messenger astronomy, gave us a symphonic view of cosmic violence no single instrument could capture alone. Here's the real kicker: the kilonova's debris didn't expand evenly. Some clumps raced ahead at slightly different velocities, creating shock waves that heated the surrounding material to billions of degrees. These turbulent bubbles glowed with the signature of freshly minted elements, like cosmic breadcrumbs leading back to one of nature's most extreme forges. By tracking these hypervelocity jets, astronomers confirmed something astonishing: kilonovae might be the universe's primary factories for our process elements, the heavy metals crucial for everything from nuclear reactors to wedding rings. It's a dazzling reminder that even the fastest, most chaotic events in space can leave behind treasures, literally sprinkling stardust across future solar systems. And somewhere in that neutron-rich debris field, there's likely enough gold to plate every planet in the Milky Way, if only we could catch it. While red dwarf stars are often considered small and relatively calm, Velocity proved they can unleash some of the most violent tantrums in the cosmos. In 2008, this unassuming red dwarf, barely a third the size of our Sun, erupted with a stellar flare so powerful it blasted charged particles into space at 25% the speed of light. That's over 270 million kilometers per hour, fast enough to reach Pluto in under 2 days. What makes this flare truly extraordinary is the sheer scale of energy involved. For just a few minutes, Velocity became 10,000 times brighter than normal, hurling enough high-energy protons and electrons to cook an entire planetary atmosphere. If Earth orbited this star, that single flare would have stripped our ozone layer in hours, bombarding the surface with lethal radiation. But here's the real shocker: red dwarfs like Velocity are among the most common stars in our galaxy, outnumbering Sun-like stars 10 to 1. Many of them host planets in the habitable zone where liquid water could exist. Yet with flares this frequent and ferocious, any potential life would face a brutal reality check. Unlike our Sun's occasional solar storms, red dwarfs can erupt multiple times a day, bathing their planetary systems in relentless radiation. Yet there's an upside to this cosmic volatility. Studying flares like Velocities helps astronomers understand space weather beyond our solar system, and how young planets might survive such hostile environments. Some theories suggest strong magnetic fields or thick atmospheres could shield life, turning these turbulent red dwarf systems into unexpected oases. One thing's certain when it comes to stellar fireworks: the smallest stars can leave the biggest scars. Storming through the cosmic void at speeds that dwarf even the most powerful hurricanes, galactic winds from starburst galaxy M82 scream across space at over 2 million miles per hour, fast enough to cross the entire United States in less than 2 seconds. This isn't just interstellar weather. It's a celestial fire hose blasting enough gas and dust into intergalactic space to forge millions of new stars. What fuels these supersonic outflows isn't gentle stellar breezes, but the frenzied birth and death of stars on a scale so intense it warps the galaxy itself. M82 produces new stars 10 times faster than our Milky Way, cramming furious stellar nurseries into its core. Supernova detonate like cosmic firecrackers, while massive stars flood nearby space with radiation. So much energy, it superheats surrounding gas until it erupts outward in these colossal winds. But here's where nature's ingenuity shines. As these scorching gusts race into the void, they carry more than destruction. They ferry the raw materials for future cosmic construction. Iron, carbon, and oxygen forged in stellar furnaces hitch a ride on this hypervelocity highway, eventually cooling into tendrils that gravity will sculpt into new stars and planets. It's a paradox: the same violence that clears out a galaxy also sows seeds for its next generation. Hubble's keen eye caught these winds in breathtaking detail, revealing glowing filaments stretching over 30,000 light-years, evidence of how far this stellar exhaust travels. Even more remarkable, similar outflows likely shaped our own Milky Way's evolution billions of years ago. So while M82's winds may seem like chaos incarnate, they're part of a grand cycle blowing where they must so that new worlds might one day rise from the storm. While most planets spin at a leisurely pace, one distant world takes rotation to mind-bending extremes, Beta Pictoris b, a gas giant whipping around its axis at 25 kilometers per second. That's more than twice Jupiter's speed, meaning a single day on this planet blurs past in just 8 hours. What makes this exoplanet such a cosmic speed demon? The answer lies in its youth. Beta Pictoris b is barely 20 million years old, practically a newborn by planetary standards. When gas giants form, they inherit rotational momentum from the swirling disk of material that birthed them. Imagine a figure skater pulling their arms in tight as the young planet contracts under gravity. Any initial spin gets amplified dramatically. But there's another twist. This planet orbits incredibly close to its star, completing a full revolution in just 22 Earth years. Such proximity means tidal forces constantly stretch and squeeze Beta Pictoris b, potentially transferring even more angular momentum into its rotation. Combine that with residual heat from its violent formation, and you've got a recipe for record-breaking spin rates. What fascinates astronomers most is how this extreme rotation distorts the planet's shape. At these speeds, centrifugal force causes noticeable flattening. Beta Pictoris b likely bulges at its equator like a cosmic beach ball squeezed at the poles. Future telescopes might even detect this oblate shape, offering clues about the internal structure of young gas giants. While Jupiter took billions of years to slow down, Beta Pictoris b reminds us that planets start out wild, spinning furiously before gravity and time gradually apply the brakes. It's a fleeting phase of planetary adolescence captured in action, a whirlwind of gas and momentum screaming through the cosmos. Woven through the Milky Way's halo like invisible rivers, vast currents of dark matter surge at 500 kilometers per second, ghostly remnants of ancient galactic feasts. These hypervelocity streams are the cosmic aftermath of our galaxy's violent past, where cannibalized dwarf galaxies left behind more than just stars. Their dark matter skeletons still course through space, mapping a history of collisions we can barely see. Enter the Gaia spacecraft, Europe's celestial cartographer, painstakingly tracking the motions of over 1 billion stars to reveal these hidden currents. By analyzing subtle stellar wobbles, Gaia exposes the gravitational fingerprints of dark matter flows twisting through our galactic neighborhood. One particularly massive stream, dubbed the Gaia Sausage, betrays a dwarf galaxy torn apart 8 to 10 billion years ago. Its stars now streaking through the Milky Way's halo at dizzying speeds, while its dark matter forms an ethereal highway beneath them. What's eerie is how these streams shape everything. Unlike visible matter, dark matter doesn't collide or slow down. It barrels through space, sculpting the galaxy's gravitational scaffolding. Stars and gas hitch rides on its currents like leaves caught in a phantom wind. Some researchers even suggest these flows might funnel rogue planets or lone black holes into the Milky Way suburbs, delivering cosmic strays at speeds no natural process should allow. Yet the real revelation lies in Gaia's maps. By reverse engineering stellar motions, astronomers can trace these streams back to their origins like rewinding a cosmic crime scene. Each twist in the data hints at another long-dead galaxy swallowed by our own, its essence now woven into the Milky Way's invisible fabric. It's a reminder that even the darkest, fastest forces in the universe leave traces if we know how to look. Even black holes have to obey the cosmic speed limit, but some push it to the absolute edge. At the heart of binary system Maxi J1820 plus 070, a stellar mass black hole spins so ferociously, its inner accretion disk whips around at 32,000 revolutions per minute, nearly 1/3 the speed of light. That's not just fast, it's a space-time vortex so intense, atoms near the edge get stretched into spaghetti by tidal forces while X-rays scream into the void. Scientists caught this extreme spin using a clever cosmic stopwatch X-ray timing. As material spirals toward the black hole, friction heats it to millions of degrees, creating erratic flickers in X-ray emissions. By analyzing these rapid pulses with satellites like NASA's NICA instrument, researchers spotted a telltale rhythm: X-rays dimming and brightening 400 times per second, a direct heartbeat of the disk's inner edge. That frequency revealed the disk's unbelievable velocity so fast, a single speck of dust orbiting there would complete 11 full loops in the time it takes you to snap your fingers. But here's where physics gets surreal. Normally, accretion disks slow down farther out, like water draining calmly near a tub's edge but churning violently near the center. Maxi J1820's disk defies convention. Its inner region isn't just fast, it warps spacetime so severely, light itself struggles to escape tangentially. Einstein's relativity predicts this. At such velocities, the black hole's spin drags space around it like a cosmic whirlpool, twisting the disk into a hypervelocity carousel. What's revolutionary about this discovery isn't just the speed record. It's proof that even in darkness, black holes leave fingerprints, violent, flickering ones. By decoding these X-ray pulses, astronomers can now weigh black holes, measure their spins, and map the chaotic physics where gravity triumphs over all else. And somewhere in that maelstrom of superheated gas, the universe whispers a truth. There's no brake pedal in the deepest reaches of space, only acceleration, screaming toward oblivion. Some cosmic events are so violent, they fling supermassive black holes across galaxies like celestial billiard balls. Take 3C186, a monster weighing 1 billion suns that's barreling through space at 7.5 million miles per hour, fast enough to cross the distance from Earth to the Moon in just 3 minutes. Hubble's jaw-dropping image reveals the aftermath. A 200,000 light-year long trail of newborn stars glowing in its wake, like a cosmic brushstroke painted across the void. This black hole didn't just drift away, it was kicked. Here's the physics behind the universe's ultimate ejection. When two supermassive black holes spiral toward merger, their final collision isn't always clean. If their spins are misaligned, the resulting blast of gravitational waves rockets the merged black hole in one direction like a cannon recoiling after firing. For 3C186, that kick was so powerful, it escaped its host galaxy's gravitational grip entirely. The real spectacle lies in its impact. As the black hole plows through intergalactic gas, it compresses and superheats the material, igniting shockwaves that trigger star formation. Those blue streaks in Hubble's image, they're clusters of young stars blazing to life in the chaos, proof that even the darkest objects can sculpt light. What's unnerving is how far 3C186 has already traveled. 25,000 light-years from its galaxy's core, it shows no signs of slowing. One day, it might drift alone through the cosmic abyss, a gravitational fugitive still carrying the echoes of an ancient collision. And it's not unique. Astronomers suspect many black holes may lurk in intergalactic space, exiled by similar violent births. The universe doesn't just create monsters, it sometimes flings them into the darkness. While most stellar explosions hurl debris at impressive speeds, few match the sheer ferocity of V959 Monocerotes, a nova whose 2012 eruption blasted stellar material outward at a mind-numbing 3,500 kilometers per second. That's not just fast, it's like launching a bullet with enough force to circle Earth's equator in under 12 seconds. What makes this explosion so special isn't just its speed, it's the cosmic partnership that triggered it. V959 Mon belongs to a rare class called symbiotic binary systems, where a white dwarf and red giant star orbit each other in a deadly dance. The white dwarf acts like a celestial vampire, siphoning hydrogen from its bloated companion until the stolen gas reaches critical mass, igniting a thermonuclear firestorm on its surface. Normally, nova eject material at a few thousand kilometers per second, But V959 Mons blast was supercharged thanks to a hidden twist, the white dwarf's powerful magnetic field. When astronomers examined radio waves from the aftermath, they found something unprecedented. The debris wasn't expanding in a simple sphere. Instead, the magnetic fields had funneled the explosion into twin jets, accelerating material to velocities far beyond typical nova. Imagine squeezing a balloon until it doesn't just pop, it fires plasma streams like a cosmic blowtorch. Here's the real surprise: symbiotic systems like this might be cosmic gold factories. The extreme conditions in these eruptions forge rare heavy elements, scattering them into space where they can eventually become part of new planets or even life. So while V959 Mons' speed record is dazzling, its true legacy might be written in the atoms it flung across the galaxy, elements that could one day end up in places no one expects. Now let's zoom out to the biggest speed demons of all: entire galaxies, locked in a cosmic demolition derby where the wreckage reveals the universe's best-kept secret. The bullet cluster isn't just a collision, it's a smoking gun, with two galaxy clusters slamming together at 4,700 kilometers per second. That's so fast, the shockwave alone could cross the distance from Earth to the Moon in under 2 minutes. But what makes this cosmic pileup truly groundbreaking isn't the visible carnage, it's what's missing. When astronomers first mapped the bullet cluster, they expected the heaviest parts, the gas clouds glowing in X-rays, to align with the most gravitational pull. Instead, they found something bizarre. The bulk of the mass revealed by gravitational lensing had sailed ahead of the gas like a phantom freight train. That mismatch was the first direct proof of dark matter's ghostly grip on the cosmos. Unlike normal matter, dark matter doesn't slow down during collisions. It barrels right through, dragging entire galaxies along like invisible puppet strings. Here's the kicker: the gas, heated to millions of degrees in the impact, created a shockwave so violent it glows in X-rays, a cosmic fingerprint of the chaos. Meanwhile, the dark matter, indifferent to the collision, kept cruising at blistering speeds, leaving the visible universe playing catch-up. It's like watching two trucks collide, only to realize most of their weight was carried by unseen carriages detached from the wreckage. This cosmic traffic accident isn't just a speed record, it's a Rosetta Stone for understanding the universe's hidden architecture. Every hypervelocity galaxy collision teaches us more about the dark scaffolding holding reality together. And somewhere in that chaos, the bullet cluster whispers a profound truth: the fastest things in the cosmos aren't always the ones we can see. At the heart of one of astronomy's most iconic remnants lies a powerhouse of pure velocity, the Crab Nebula's Pulsar, whipping charged particles to an astonishing 1,500 kilometers per second. This isn't just a stellar ghost, it's a cosmic particle accelerator, slinging electrons and positrons into space with enough energy to light up an entire nebula. The secret: a magnetic field trillions of times stronger than Earth's, spun into a frenzy by a neutron star rotating 30 times every second. But the real magic happens in the nebula's shimmering filaments. Those glowing tendrils aren't just debris, they're highways for hypervelocity particles, energized by the pulsar's relentless wind. As these particles spiral along magnetic field lines, they emit synchrotron radiation, painting the nebula in vivid blues and purples. It's like watching a cosmic Van Gogh, where every brushstroke is a streak of matter moving faster than a thermonuclear blast. What's wild is how this local phenomenon connects to something much larger: the Fermi bubbles. These gargantuan structures stretching above and below the Milky Way's disk are essentially the Crab Nebula's big brothers, powered by similar processes on a galactic scale. Just as the Crab's pulsar wind energizes its surroundings, our galaxy's central black hole may have once spewed jets of high-speed particles, inflating these gamma-ray balloons. The difference: the Crab's winds could cross the Atlantic in a second. The Fermi bubbles, they'd need a few million years. Here's the twist: the Crab Nebula isn't just a speedster, it's a time capsule. The light we see today left the nebula in the year 1054, when Chinese astronomers recorded its supernova explosion. Every photon, every streak of high-velocity particles is a message from the past, showing us how a dying star's fury can echo across centuries. And somewhere in that storm of particles, there's a lesson: nature doesn't just create beauty, it propels it at speeds that defy imagination. Streaking through the Milky Way's halo like a rogue comet, an enormous cloud of gas known as HVC 040+01-282 is hurtling toward our galactic plane at 450 kilometers per second, fast enough to cross the entire United States in less than 10 seconds. This isn't just another wispy interstellar cloud, it's a high-velocity cosmic bullet carrying enough hydrogen to forge hundreds of thousands of suns. High-velocity clouds like this are among the galaxy's most enigmatic travelers. Some may be intergalactic strays captured by the Milky Way's gravity as they drifted through the void. Others could be the splattered remains of dwarf galaxies torn apart long ago, their gas flung outward in chaotic streams while their stars were absorbed into our galaxy's halo. But HVC 040's trajectory holds a clue. Its path traces back to the Magellanic Stream, that colossal river of gas trailing our neighboring dwarf galaxies. This suggests it might be a fragment of that same celestial current, ripped free by tidal forces and now plunging toward the galactic disk like a meteor. What happens when such a high-speed cloud collides with the Milky Way's denser gas layers? The results are spectacular shockwaves compress the incoming hydrogen, triggering cascades of star formation. It's like throwing a stone into a pond, except the ripples here ignite stellar nurseries. Some astronomers suspect our own solar system might owe its existence to a similar impact billions of years ago, a serendipitous crash that seeded the ingredients for future planets. Yet these clouds aren't just building blocks, they're also cosmic fossils. Their chemical makeup, rich in primordial hydrogen and helium with barely a trace of heavier elements, suggests they've barely mixed with the Milky Way's polluted interstellar medium. Studying them is like finding untouched ice from the early solar system, a pristine sample of the universe's raw materials. So while HVC 040 screams toward its galactic rendezvous, it carries more than just gas. It holds a piece of the cosmos's ancient, undisturbed history. While most asteroids in our solar system follow predictable orbits, sometimes the cosmos throws us a curveball, or in this case, a cosmic fastball. Meet Oumuamua, the first known interstellar visitor to our neighborhood, streaking through space at a staggering 196,000 miles per hour, so fast it could cross the distance between Earth and the Moon in just under 2 hours. What makes this mysterious object truly bizarre isn't just its speed, it's its origin. Unlike regular asteroids bound by the Sun's gravity, Oumuamua came from another star system entirely, making it the ultimate cosmic hitchhiker. When astronomers first spotted it in 2017, its trajectory told a clear story. This wasn't a local. Its hyperbolic path, an open curve rather than a closed loop, meant it had enough velocity to escape the Sun's pull and continue its journey into the unknown. But here's where things get even stranger. Most solar system asteroids top out around 120,000 miles per hour. Oumuamua blew past that like a race car lapping traffic, and it wasn't just coasting. Observations suggest it actually accelerated as it left the inner solar system, something normal space rocks simply don't do. Some theories propose outgassing sunlight heating trapped gases that then jet outward like a weak thruster. Others, more controversially, speculated about artificial origins, though the likeliest explanation remains natural, just not something we've seen before. What's fascinating is how this interstellar speedster compares to our own asteroids. Take Bennu, for instance, a solar system resident that orbits at a leisurely 63,000 miles per hour. Even the fastest known local asteroid, 2001 FO32, maxes out at 77,000 miles per hour. Oumuamua wasn't just faster, it was in a different league entirely, a true interstellar bullet that left our most familiar space rocks in the dust. The real shame, we only had weeks to study it before it vanished into the void. Future telescopes like the Vera Rubin Observatory might catch more of these fleeting visitors, helping us unravel whether Oumuamua was a rare oddball or just the first of many cosmic speedsters passing through our celestial backyard. One thing's certain, when the next interstellar traveler arrives, we'll be watching, and this time we might just get a clearer look at the universe's fastest flying rocks. Now let's shift our gaze to one of the most energetic particle accelerators in existence, not built by humans, but by nature itself. In the constellation Orion, 4 billion light-years away, a supermassive black hole powers TXS 0506 plus 056, a blazar whose jets blast material into space at 99.5% the speed of light. But what makes this cosmic flamethrower truly special isn't just its speed, it's what's hidden inside those ultra-relativistic jets. A torrent of ghostly subatomic particles called neutrinos fired across the universe like cosmic bullets. When the Ice Cube Neutrino Observatory, buried deep in Antarctic ice, detected a high-energy neutrino in 2017, astronomers traced its origin straight back to this monstrous blazar. Here's how they did it. Ice Cube's sensors don't see neutrinos directly. Instead, they wait for the rare moment one collides with an atom in the ice, producing a telltale flash of blue light called Cherenkov radiation. By analyzing the angle and timing of these flashes across its grid of detectors, Ice Cube can reconstruct the neutrino's path across the cosmos like intergalactic forensics. What's astonishing is the sheer power behind this intergalactic signal. The neutrino Ice Cube caught carried over 300 trillion electron volts. That's 45 times more energy than protons in the Large Hadron Collider. And its source, a jet so intense, it's likely filled with shockwaves where magnetic fields whip particles to near light speeds, smashing them together until they spit out neutrinos as byproducts. Imagine a celestial ping-pong match where protons ricochet so violently, they shred into these ethereal particles mid-flight. But here's the twist: neutrinos barely interact with matter, which means trillions pass through your body every second unnoticed. Catching one at all is like spotting a single specific grain of sand on all the world's beaches. That this particular neutrino traveled 4 billion years without deflection, then slammed into Ice Cube with enough precision to pinpoint TXS 0506 as its origin, is a statistical miracle. It's proof that even the faintest cosmic whispers can carry the echoes of the universe's most extreme environments, and the implications are staggering. By linking neutrinos to blazars, we've opened a new window onto the high-energy universe, one where invisible particles become messengers from the most violent frontiers of spacetime. Every neutrino Ice Cube catches is like a postcard from a black hole's jet, stamped with secrets about how nature's most powerful engines operate. So while light shows us the cosmos, neutrinos might just reveal its darkest, most energetic truths. Gravity waves don't just ripple through space, sometimes they scream. On September 14, 2015, the universe delivered proof with GW 150914, the first gravitational wave ever detected. This wasn't just any cosmic tremor, it was the death spiral of two black holes, each 30 times the mass of our Sun, merging in a finale so violent, their final moments clocked in at 60% the speed of light. That's 360 million kilometers per hour, a velocity where time itself distorts. LIGO detectors captured the signal as a rising chirp, a fleeting wobble in spacetime lasting just 0.2 of a second. But hidden in that blip was a story written in relativity's purest form. As the black holes circled each other thousands of times per second, their insane velocity warped the fabric of reality, emitting gravitational waves with the power of 3 solar masses converted into pure energy. Then, in the last 5 milliseconds, they collided. That impact didn't just shake space-time, it momentarily made the entire detector system vibrate by less than a proton's width, a whisper so faint it took Einstein's equations to decode its cosmic roar. What's astonishing isn't just the speed, but the precision of the aftermath. The merged black hole recoiled like a cannon, shooting through space at 150 kilometers per second, yet another hidden velocity etched into the signal. And that iconic chirp, it's now a Rosetta Stone for astrophysics, proving black holes don't just orbit, they dance, they accelerate, and in their final microseconds, they rewrite the rules of motion itself. Visualizing the event reveals even more surreal details. Simulated renderings show the black hole's event horizons stretching into teardrops as they spin. Their mutual gravity launching ripples that stretch and compress spacetime itself. For a fraction of a second, their orbital velocity approached relativistic limits, proving nature's most violent events aren't just fast, they're physics stripped to its most extreme fundamentals. And thanks to LIGO, we didn't just hear it, we measured the universe's heartbeat in the key of gravity. The Milky Way isn't just a static swirl of stars, it's a living, breathing ecosystem with its own weather system, complete with hypervelocity storms. Picture this, vast rivers of superheated gas, each one moving at over 1 million kilometers per hour, cycling between the galactic disk and its halo like a cosmic fountain. These aren't random gusts, they're the galaxy's way of regulating its own star formation, turning the raw materials for new suns into an interstellar recycling program on the grandest scale. At the heart of this phenomenon are dying stars and supernova, nature's demolition crews. When massive stars explode or expel their outer layers, they blast enormous bubbles of hot gas into the galactic disk. Like steam rising from a boiling pot, this material surges upward, carrying heavy elements forged in stellar cores. But gravity eventually wins, pulling the cooling gas back down in colossal droplets that rain onto the disk below. Each droplet carries the seeds of future stars, and the cycle begins anew. What's fascinating is how this process acts as the galaxy's thermostat. When star formation runs too hot, supernova eruptions pump gas out of the disk, slowing the birth of new stars. But when things cool down, the returning gas reignites the process. It's a delicate dance of creation and destruction, one that ensures the Milky Way doesn't burn through its fuel too quickly or stall entirely. The sheer scale of these flows is staggering. Imagine a single fountain loop stretching tens of thousands of light years, with enough gas in motion to build millions of stars. Telescopes like Hubble have even spotted similar processes in other galaxies, their halos glowing with the faint light of these falling rainstorms. So the next time you gaze at the night sky, remember what looks like stillness is actually a galaxy in constant, high-speed flux, breathing in and out across eons. Some duos in the universe take inseparable to astonishing extremes, but none push the limits like the white dwarf binary Cancri. Imagine two dead stars, each more massive than our Sun, yet crammed into a space smaller than Earth, whipping around each other at 1.8 million kilometers per hour. That's so fast, they complete an entire orbit in just 5 minutes and 21 seconds faster than most popcorn kernels pop in your microwave. What makes this cosmic tango so fascinating is how these stellar remnants got so dangerously close. Normally, binary stars age gracefully apart, but Cancri tells a different story. Billions of years ago, these were ordinary stars orbiting each other at a safe distance. When one expanded into a red giant, it engulfed its partner in a messy stellar embrace. Friction then dragged the smaller star inward, stripping away the giant's outer layers until only its dense core remained. The same dance repeated when the second star reached old age, leaving behind two white dwarfs locked in a gravitational death grip. Now, their breakneck orbits do more than set records, they serve as a cosmic laboratory for Einstein's predictions. Every rotation sends ripples through spacetime itself, gravitational waves that slowly sap their orbital energy. Calculations show this system loses about 1.4 meters per year as those invisible waves carry momentum away. Given enough time, roughly 300,000 years, these white dwarfs will collide. Depending on their combined mass, that crash could trigger a dazzling supernova or forge an even denser neutron star. The real magic lies in what H.M. Cancri teaches us about stellar evolution's most extreme paths. Most white dwarfs fade quietly into cosmic history, but binaries like this rewrite their own endings through sheer velocity. As astronomers track their rhythmic light flickers with millisecond precision, each observation peels back another layer of how gravity operates under conditions no lab could ever replicate. It's a reminder that even in death, stars can create some of the universe's most breathtaking spectacles, not with explosions, but with speed itself. In the chaos of a cosmic demolition zone, where shockwaves from dying stars pile up like interstellar traffic jams, one structure stands out: the N44 superbubble. Spanning over 1,000 light-years in the Large Magellanic Cloud, this colossal shell of gas races outward at 125 kilometers per second, fast enough to cross the continental United States in under a minute. But what makes N44 truly spectacular isn't just its speed, it's the engine behind it. Not one, but multiple supernovae detonating in sequence, each blast pushing the bubble's walls farther into space like a runaway snowplow clearing a galactic highway. Multi-wavelength images reveal the superbubble's violent beauty in stunning detail. X-rays paint the scorched interior where gas burns at millions of degrees, while visible light glows along compressed ridges of hydrogen, lit up like neon signs by the radiation of young, massive stars. Infrared peels back the veil entirely, exposing tendrils of dust forged in the very explosions that power this expansion. It's a fossil record of stellar chaos, each layer a timestamp of another supernova's fury. Here's where physics gets wild. Unlike a single supernova's spherical blast wave, N44's shell is lumpy and asymmetrical, a testament to the messy reality of clustered star death. Some regions surge ahead where multiple shockwaves overlap, while others lag where energy dissipates into the void. This isn't just an explosion, it's a cascading demolition where each supernova stacks on the last, building momentum across generations. But the real magic lies in what N44 leaves behind. Those compressed gas walls, they're stellar nurseries. As the shockwaves plow through space, they trigger turbulence dense enough to collapse into new stars, some of which will eventually explode, fueling the next cycle of expansion. It's a self-perpetuating engine of creation and destruction, proving that even the fastest cosmic structures aren't just tearing through space, they're reshaping it for the future. Deep in the constellation Sagittarius, a cosmic powerhouse once spun faster than any kitchen blender, SGR 180620, a magnetar boasting 30,000 rotations every single minute. That's a full revolution every 2 milliseconds, so fast its surface moved at nearly a quarter the speed of light. This wasn't just a rapidly spinning neutron star, it was a ticking time bomb wrapped in the strongest magnetic field ever measured, a quadrillion times more powerful than Earth. Then, on December 27, 2004, it detonated. In a tenth of a second, SGR 180620 unleashed a hyperflare so bright, it temporarily ionized Earth's upper atmosphere from 50,000 light-years away. The energy released was equivalent to what our Sun radiates in 150,000 years, all focused into a single, catastrophic burst. But here's the twist. That explosion didn't just light up the cosmos, it slammed the brakes on the magnetar's dizzying spin. Astronomers caught the aftermath in real time. The hyperflare's sheer force ejected material asymmetrically, creating a recoil effect that slowed the star's rotation by a measurable fraction. It's called magnetic braking, a phenomenon where a magnetar's own ultra-powerful field acts like an anchor in space, sapping its spin energy over time. Imagine a figure skater extending their arms to slow down, except here the arms are magnetic field lines so intense they distort the shape of atoms themselves. What's fascinating is how magnetars like this rewrite the rules of physics. Most neutron stars gradually slow as they age, but SGR 180620's deceleration was abrupt, a cosmic whiplash from its own violent outburst. And while it's no longer the fastest known magnetar, it left behind a critical clue. These ultramagnetic monsters don't just spin wildly, they can literally tear themselves apart with their own energy. Every flare, every slowdown is a page in the playbook of how matter behaves under conditions we can't possibly replicate on Earth. So while SGR 180620 may have lost its title, its legacy lives on a reminder that in the universe's most extreme environments, even the fastest rotators can't escape the grip of their own magnetism. And somewhere out there, another magnetar might already be winding up for its own record-breaking performance. Tucked away in the Milky Way's shadowy outskirts, something strange is happening. Our galaxy's outer halo spins at a brisk 220 kilometers per second, dragging stars and gas along invisible currents. This isn't just any rotation, it's a cosmic tug-of-war between two competing explanations: the gravitational pull of dark matter or the possibility that gravity itself behaves differently on galactic scales. Here's the puzzle. Newton's laws predict that stars farther from a galaxy's center should orbit slower, like planets in our solar system. But when astronomers mapped the Milky Way's outer reaches, they found stars whipping around just as fast as those near the core. The simplest solution: a massive halo of dark matter enveloping the galaxy, its unseen gravity propping up those unexpected speeds. Think of it as an invisible hand gripping a spinning top. Without it, the outer stars would fly off into the void. Yet some scientists propose a radical alternative. What if dark matter doesn't exist at all? Modified Newtonian dynamics, or MUND, suggests gravity strengthens slightly at vast distances, eliminating the need for invisible particles. It's like realizing the top spins fine, you just misread the instructions. Supporters point to certain dwarf galaxies where MUND predictions align neatly with observations, no dark matter required. But the Milky Way's halo tilt throws a curveball. Detailed velocity maps reveal subtle twists in the outer rotation patterns that resemble dark matter's gravitational fingerprints. Simulations show these kinks naturally emerging from clumps of invisible matter swirling in the halo, while MUND struggles to replicate them. It's as if the universe left two competing blueprints, and we're still deciphering which one matches the building. What's at stake goes beyond astrophysics textbooks. If dark matter's the answer, its nature could rewrite particle physics. If MUND prevails, Einstein's relativity might need an update. For now, the Milky Way's silent spin holds the clue, a reminder that even the fastest motions in the cosmos can hide the deepest mysteries. Hurtling through the cosmos at unimaginable speeds isn't just reserved for stars and black holes. Some exoplanets have atmospheric chaos that puts even Jupiter's great red spot to shame. Take HD 189733b, a cobalt-blue gas giant where winds scream across the equator at 8,700 kilometers per hour, 7 times the speed of sound, and fast enough to cross the Atlantic Ocean in under 30 minutes. Scientists pieced together this exoplanet's violent weather using a clever celestial fingerprinting technique called Doppler mapping. Here's how it works. As HD 189733b orbits its star, its atmosphere absorbs and scatters starlight in distinct ways. By analyzing subtle shifts in the light's wavelength, like listening to a siren's pitch change as it moves toward or away from you, astronomers can trace the movement of gases in the planet's atmosphere. The result, a wind map of an alien world 63 light-years away, revealing jet streams that could shred metal like tissue paper. But what fuels these supersonic winds? The answer lies in extreme temperature contrasts. Tidally locked to its star, the planet's day side broils at 930 degrees Celsius, while its night side remains hundreds of degrees cooler. This thermal imbalance creates a pressure cooker of atmospheric circulation, with heated gases exploding toward the colder hemisphere at velocities that dwarf Earth's strongest hurricanes. Infrared observations add another eerie layer. Silicate particles detected in the atmosphere suggest these winds carry microscopic shards of molten glass raindrops forged in a furnace, then hurled sideways fast enough to sandblast anything in their path. It's a reminder that when it comes to cosmic weather, speed isn't just about motion, it's about the sheer, unfiltered violence of an alien environment we're only beginning to understand. Even black holes have to work for their meals, and when they rip apart a star, the results are spectacularly violent. Take Assassin 14, Lie, a tidal disruption event so extreme, it launched stellar debris outward at 30,000 kilometers per second, 1/10 the speed of light. This wasn't just a cosmic snack, it was a full-blown stellar massacre captured in real time by X-ray telescopes that caught echoes of the carnage reverberating through space. Here's how it happened. A star drifted too close to a supermassive black hole, roughly 3 million times heavier than our Sun. The black hole's gravitational tide stretched the star into a spaghetti-like strand, a process called spaghettification, before violently shredding it apart. But here's the twist, not all that stellar material fell into the abyss. Some got slingshotted outward in jets of superheated plasma, accelerated to relativistic speeds by magnetic fields twisting around the black hole's poles. The real breakthrough came when astronomers detected X-ray reverberation, delayed flashes bouncing off debris swirling just outside the black hole's event horizon. These cosmic echoes acted like sonar, mapping the chaotic environment in ways never before possible. For the first time, scientists could track how material spirals inward, gets flung outward, and even warps spacetime in the process. What's truly mind-bending is the sheer energy involved. The debris racing away at 10% light speed carried enough kinetic energy to outshine an entire galaxy for weeks. And hidden in that high-speed wreckage, clues about how black holes grow, how they shape their host galaxies, and even how they might fling precious heavy elements back into the cosmos. So while Assassin 14, Lie might sound like a cosmic demolition derby, it's also a rare glimpse into the messy physics of gravity's darkest giants, where even destruction can light up the universe with answers. Now let's turn our attention to a different kind of cosmic speed, one that sculpts entire galaxies like an invisible potter's hand. At the heart of the stunning barred spiral NGC 1300, a colossal density wave races through its arms at 300 kilometers per second, so fast it could circle Earth's equator in under 2 minutes. But this isn't just motion for motion's sake, it's the engine behind one of the most mesmerizing structures in the universe. NGC 1300's grandeur comes from a delicate balance of forces. Its central bar, a thick lane of stars stretching 26,000 light-years, acts like a gravitational traffic circle, funneling gas and dust inward. As this material piles up, it triggers bursts of star formation, illuminating the spiral arms in a dazzling display. Meanwhile, the density wave sweeps through like a cosmic comb, compressing interstellar gas as it goes. That compression ignites new stars ahead of the wave, while older stellar populations trail behind, creating the galaxy's iconic, leading blue arms and trailing golden core. What's fascinating is how this speed holds the galaxy together. Without the density wave's relentless motion, NGC 1300's spirals would wind tighter and tighter over time, eventually blurring into a featureless disk. Instead, the wave's 300 km/s march maintains the galaxy's structure, balancing gravity's pull with centrifugal force. It's nature's way of preserving beauty on a galactic scale, an eternal dance between chaos and order. Barred spirals like this also hold a secret about galactic evolution. The bar's rotation channels material toward the supermassive black hole at the center, feeding it in sporadic bursts. Over eons, this process may determine whether a galaxy remains active or falls quiet. NGC 1300's breakneck wave speed suggests its dynamics are particularly efficient, a cosmic conveyor belt shuttling fuel toward the center at a staggering pace. So while black holes and neutron stars dominate the speed records, let's not overlook the quiet power of density waves, architects of spiral galaxies, shaping starry arms with nothing but gravity and motion. In NGC 1300, 300 kilometers per second isn't just a number, it's the rhythm of creation itself. Tucked away in the monstrous heart of galaxy M87, a rogue star cluster just didn't belong, it was moving too fast. HVGC1, a tightly packed family of ancient stars, was caught in the act of escaping its galactic home at 3.4 million miles per hour. So fast, Hubble's proper motion observations showed it had already crossed a distance equal to the Moon's orbit around Earth in just 19 minutes. What makes this globular cluster's escape so extraordinary is the sheer impossibility of it all. These stellar swarms typically orbit galaxies like bees around a hive, held firm by gravity's grip. But HVGC1, it's a cosmic bullet fired from the most powerful gun imaginable, the supermassive black hole at M87's core. Here's the twist, it wasn't ejected alone. Simulations suggest this cluster survived a gravitational heist where a freak encounter with two black holes, a binary pair, slingshotted it outward like a stone from a double-barreled catapult. Hubble's images reveal the smoking gun. HVGC1's trajectory points straight back to M87's center, where the black hole duo likely still lurks. The energy required to launch an entire cluster, hundreds of thousands of stars bound together, defies belief. Yet there it streaks, a glittering relic of chaos, now destined to drift forever in the void between galaxies. What's haunting is the fate of its stars. Unlike hypervelocity stars ejected solo, HVGC1 stars remain shackled together by their own gravity, a nomadic tribe carrying the DNA of their violent birth. They'll never form new generations, just slowly fade as they voyage through the cosmic dark, a silent testament to the black hole's ruthless power. And somewhere in their ancient light lies a lesson: even the universe's fastest objects aren't always lone wolves. Sometimes they escape together. Some cosmic explosions don't just announce their arrival, they scream it. When supernova SN 2008D erupted in galaxy NGC 2770, it did something unprecedented. It flashed a pulse of X-rays so intense, astronomers caught the exact moment its shockwave blasted free from the dying star at 46,000 kilometers per second, nearly 1/6 the speed of light. This wasn't just a supernova, it was the universe pulling back the curtain on stellar death's first violent heartbeat, captured in real time for the first time. The magic happened during what astronomers call a shock breakout, stellar physics' most fleeting spectacle. When a massive star exhausts its nuclear fuel, its core collapses in milliseconds, rebounding as a supersonic shockwave. But here's what's wild: that shock doesn't instantly exit the star. It plows through dense outer layers like a bulldozer fighting quicks and heating gas to billions of degrees until, bam, it punches free, releasing a blistering X-ray flash brighter than a billion suns. That's the moment telescopes caught with SN 2008D, a cosmic freeze frame of destruction traveling fast enough to cross Earth's diameter in under a second. What makes this shockwave special isn't just its speed, it's the forensic clues it left behind. The X-ray burst lasted only 5 minutes, but its spectrum revealed fingerprints of the star's final moments. Nickel, cobalt, and iron elements forged in the collapsing core were already present, proving the shock had cooked its way through fresh nuclear ash. And the star itself, analysis suggests it was a Wolf-Rayet type, a rare heavyweight that had already shed its outer layers, letting the shock escape faster than in bulkier stars. But here's the twist: SN 2008D wasn't just a fireworks show. Its shock breakout confirmed decades of supercomputer models, giving physicists real-world data on how dying stars recycle elements into space. Every atom in your body once rode such a shockwave, a hypervelocity courier delivering the building blocks of planets and life itself. So while the flash faded in moments, its legacy echoes across cosmic time, proof that even in destruction, stars race to light the way for what comes next. We've reached the final speed record in our cosmic countdown, one that doesn't just break the mold, but stretches the very fabric of the universe itself. Meet GNZ 11, the most distant galaxy ever confirmed, hurtling away from us at an almost incomprehensible 295,000 kilometers per second. That's 98% the speed of light, so fast, if you could somehow chase it, time itself would slow to a crawl for you relative to the rest of the cosmos. But GNZ 11's record-breaking velocity isn't just about raw speed. It's a time capsule from 13.4 billion years ago, when the universe was a mere 400 million years old. The light we see today left this galaxy when cosmic dawn was still breaking, and its frantic recession rate reveals something startling. Space itself is expanding faster the farther back we look. Here's where things get controversial. According to our best measurements of today's universe, galaxies like GNZ 11 shouldn't be receding this quickly. This mismatch between ancient and modern expansion rates is called the Hubble tension, and it's currently one of astrophysics' greatest puzzles. Some theorists suggest undiscovered dark energy properties might be at play, while others entertain even wilder ideas like cracks in our understanding of gravity itself. What's undeniable is that GNZ 11 forces us to rethink cosmic history. Its extreme redshift Z equals 11.09 acts like a speedometer written in light, proving the early universe was stretching at rates that challenge our models. Every photon that reaches us from this galaxy has been stretched 12-fold by expansion, morphing once visible light into infrared whispers only telescopes like Hubble and JWST can decode. So while GNZ 11 may hold the title for the fastest recession we've ever measured, its true legacy lies deeper. It's not just racing away, it's pulling the curtain back on one of the universe's oldest secrets, that even the vacuum of space itself has a need for speed, and we're only beginning to understand why. As we cross the finish line of our cosmic speed tour, let's revisit 5 record breakers that redefine what fast even means in the universe. Topping the charts is Pulsar J 1748-2446 AD, the neutron star spinning 716 times per second, so rapid, its surface moves at nearly a quarter light speed. Close behind, the oh my god particle, a single proton screaming through space at 99,999,999,999,999,951% the speed of light, carrying energy that still baffles physicists. Not to be outdone, hypervelocity star S5 HVS1 barrels through the Milky Way at 1,755 km/s, flung by our galaxy's central black hole like a gravitational slingshot. Then there's Blazar TXS 0506 plus 056, whose jets hurl neutrinos across billions of light-years at near-light speeds, proving even ghostly particles can become cosmic bullets. And who could forget GNZ 11, the most distant galaxy we've spotted, racing away at 98% light speed as the universe's expansion stretches space-time itself. These phenomena aren't just breaking records, they're shredding the rulebook of physics. From warped space-time around pulsars to particles flirting with light speed limits, each one forces us to rethink what's possible. Einstein's relativity gets stretched to its limits, dark matter's influence reveals itself, and even the vacuum of space becomes a drag strip. But here's the thrilling part. For every speed demon we've caught, there are countless others still lurking in the cosmic shadows. Could there be neutron stars spinning even faster, buried in dense star clusters? Might some undiscovered particle be nipping at light speed's heels right now? That's where you come in. Drop your wildest theories in the comments. What cosmic speedsters do you think are still waiting to be found? And if you're hungry for more mind-bending space mysteries, hit subscribe. We're just getting started on exploring the universe's most extreme frontiers, where the laws of physics don't just bend, they shatter. Until next time, keep looking up and hold on tight. The cosmos loves a speed bump.